I am the Assistant Director of our Additive Manufacturing Department here at Saratech. I've been with Saratech for 4 years, and I help customers engineer better products with the help of additive manufacturing solutions. So today's session is going to be very fun. We're going to dive into some of the advanced features within Eiger. Now, Eiger is Markforged's slicing software, file preparation software for the Markforged printers. And this session is going to assume that you have some basic familiarity with Eiger already. If you don't, not to worry, we have a great YouTube tutorial on some of the basics of getting your parts into Eiger and getting printing with it. But if you are new to it, still stick around. We're going to have some interesting topics that will be of great use to you guys later. And if you don't have a Markforged printer or even know what Eiger is, that's okay too. A lot of the topics we'll talk about today are also applicable to other types of FDM or FFF technologies. So with today's session, we're going to cover three topics, which are going to be the advanced fiber routing. Now, Markforged printers do route continuous fibers within their parts, which make them extremely strong. And we're going to talk about how to get the most out of that feature and how to route your fiber where you need it and keep it out of places you don't need it. Next, we're going to talk about creating support overrides. Now, supports are sometimes an unavoidable part of 3D printing, but we can gain a little bit more control over where we put those supports in our parts. So we'll see how we can do that as well. And then the last topic we'll talk about is pause at layer height and why you would want to do this. So pausing at a layer height enables you to embed hardware into your parts, which gives you greater usability. And we'll see some ways we can do that. So let's go ahead and jump right into it, talking about advanced fiber routing. So on the right here, we have some parts that are with a transparent nylon, and you can see the fibers routed around the parts. And that's what makes Markforged printers unique, is that they're the only printer out there that can route continuous strands of fiber, either fiberglass, Kevlar, or carbon fiber within the parts. And that's really great because with the Markforged's material Onyx, which is their base nylon material, when you reinforce that with carbon fiber, you can get parts as strong as 6061 aluminum, which is absolutely amazing. We've seen such great success with our customers replacing machined aluminum parts with these Onyx and carbon fiber parts, and it has saved them such great time and basically it's sped up, if they're doing a project where they need some work holding fixtures or whatever to make their parts, it's rapidly accelerated their process by being able to 3D print that instead of machining it out of aluminum. Now, one of the caveats to that great technology is that it is an FFF or an FDM process, meaning that it is going to build up in the Z direction. So the print head will move in the XY plane, and then once that plane has been printed, the plastic's been deposited, the printer will move up just a tiny bit in the Z direction and continue over and over. So that does lead to one downside, which is that the Z seam or the Z direction tends to be the weaker direction of the part. That's because you have layer on top of layer, and that interlayer adhesion is not quite as strong as the material itself. So with very long, thin, tall parts, they are at risk of breaking. So that's one important thing to note as we get into the advanced fiber routing. The other caveat to that as well is that with the fiber reinforcement, it is continuous, but it is continuous in the XY plane. So there really is no way to get a strand of fiber that's in the bottom plane connected all the way up to the top plane. So while that may seem like a downside, we'll talk about how we can get around that and how it really won't affect us with the correct part orientation here. So let's first talk about carbon fiber and how it's used. And carbon fiber, or any fiber really that we're going to talk about, is going to be strongest in tension. So if you have a part that's being pulled, you want to orient those fibers in the direction of the tension to get the most strength out of it. Now, that may not always be your loading case. So another very common loading case is bending. A lot of parts we make are going to be experience some sort of bending force. Now, with a part that's bending, we still have tension to some degree. That's because if you take a look at the bending theory, you'll see there is a neutral axis where the part is being bent around, and on top of that neutral axis, you'll have some compression. If you're bending it upwards like that, you'll have compression on the top, but then you'll have the tension in the bottom. So when you have this case, which is a very common case, the best thing to do is make a carbon fiber sandwich, if you will. So you have carbon fiber at your top, carbon fiber at your bottom, and then the neutral axis doesn't really need it because not as many forces are going to be on that neutral axis. And then the last case, which is a little tougher to deal with, would be compression. Of course, the carbon fiber won't be as strong in compression as it would be in tension, but it can still act as kind of like a scaffold when your part is being compressed. So with that being said, there are multiple ways we can add the fiber to the part, to that specific layer. We can do what's called an isotropic fill, which we have here on the far left. And an isotropic fill is basically going to route the fiber pretty much throughout the entire layer as tightly as it can. And then on the next layer, it's going to take that angle and alternate it by 45 degrees. And it's going to keep doing that 45 degrees. So you get fibers that are crisscrossing over one another. And that's generally going to give you the best strength if you're trying to make your carbon fiber sandwich, if you will. And then the other methods of routing fiber would be a concentric fill. And concentric fills basically follow the profile of the part. So they'll go either around the perimeter and the inner walls, or you can be selective and tell it I want it on the outer shell only or on the inner holes only. Inner holes is great if you need to put bolts through a part and you want the bolts, the holes to be reinforced. That's when you'd use something like that. So let's go ahead and jump into Eiger and see how we would do that. So I have a sample part here, and this part is it's made for this demo, but it represents a typical bracket or something you might be using. And as you can see here, we have a hole going through here, two mounting holes where something could potentially be bolted on here. And as you could imagine, this part is going to experience some sort of bending. So really, when we're talking about 3D printing parts, the first thing you want to do is keep your manufacturing process in mind. So since we're doing additive manufacturing, we're going to do some things to increase the part strength. One would be a chamfer right here. Now, when you're machining parts, fillets, chamfers, they are additional operations. They add to the cost and complexity of that part. But with 3D printing, complexity comes for free. We can add chamfers, fillets. It doesn't add much print time at all, and it doesn't add any complexity for the operator. So if we can add a feature like a fillet to reduce stress concentrations, go ahead and do it because it's not going to make your life any harder. Now this part here is obviously on the build plate here, and it's going to be built up in the Z direction here. Now that is going to present us an issue because, as we talked about before, the Z strength is an issue with FDM parts. So if we're pushing on the top of this part here, it could break somewhere down here on the edge because of the Z layers. So one way to counteract that would be to put it on its side here. Now the layers are basically running. The Z direction is up in this direction here, so we're not putting the layers in the against where there's going to be load. So naturally the part's going to be stronger when we do it this way. But we want this part to be really stiff. We want it to be as strong as aluminum. So we're going to go ahead and turn on our carbon fiber reinforcement here. And when we do that, we'll hit save. It's going to go ahead and by default put it in the top and bottom of our part. But everything we're going to be doing in today's session is going to revolve around this X-ray environment here. Now, X-ray allows you to see the actual pathing of the tool head, of the print head, and how it's going to put down those layers. So you can actually see here, this is a layer by layer of how the part's being printed. So in this layer view, the blue represents our carbon fiber, and the support structures, which we'll talk about in a little bit, is represented in this purple color here. So let's talk about the carbon fiber. Well, right now you can see it is creating an isotropic fill at the top and bottom. And we know it's isotropic because it says it's isotropic here. And if we take a look, I'm going to switch over here. We have a 3D and a 2D view. We'll put it in the 2D view. We can see here that the fiber is being routed at one angle here. And then if we go back a layer, it gets routed with an alternating angle like that. So we want to make this part resistant to bending. And if we're talking about bending, see now we're looking at the side of the part. So imagine this plane right here is going to be pinned down to something, maybe bolted down, and then this part sticking up is going to receive the force. So again, we have a bending situation where straight through the middle of the part here, we have our neutral axis and we don't really need carbon fiber there. So we're going to go ahead and change this into a concentric fiber fill. And when we do that, we can hit apply changes and we see that now it's only applying carbon fiber to the outer layers. But if we go back to our part, we can see, well, we only have carbon fiber at the bottom and the top, and a sandwich is not really applicable here because we're not bending in that direction. We're bending in this direction here. So we need more fiber up along the part. So the way we can do that, we can add additional regions of fiber. So I can just select a region here and I can click create new override and add a fiber to that region. And then again, I'll have the same options, whether I want to do an isotropic fill, a concentric fill. I can even change how many times we go around the perimeter. So right now we're making 2 loops, as you can see, around the perimeter, but we can increase that to 3 as well. And you can see I hit apply and it adds a third loop around the perimeter there. But for this part, I need it really, really stiff. And I want carbon fiber going pretty much evenly distributed throughout the length of the part. So I'm going to take this region here of carbon fiber and let me just delete that and start from the beginning. So the way you'd add fiber, like we just saw, is you click, you drag, and I'm going to select the entire part right here. I'm going to click create new override, add fiber, and change it to a concentric fill like we discussed here. Now this can take a little bit of time if you have a large part, so just be patient with it. The nice thing about Eiger is that it is cloud-based, so these calculations are not running on your computer, but they're actually running on Markforged's computers in the cloud, so you can close this page and come back to it when it's done. So we can see here now we've added fiber throughout the entire part. Now, if we do add it to the entire part, it will add to our cost here. And if we let this calculate out, we'll see the updated cost comes to $53, which is not too bad, definitely cheaper than machining a part out of aluminum. In this case, you know, we want it strong, but maybe it doesn't need every single layer to have fiber. So one thing that we can do is called striping. So instead of doing it through this entire region, we can change it to stripes. And stripes add evenly spaced regions of fiber throughout the part. So for this one here, let's just pick an arbitrary number. Maybe we do 10 stripes. Well, on the bottom here, we can see that this part contains a total of 480 layers. So let's just say we want maybe only 100 of those layers to have fiber in them. So we'll say we have we want 25 regions with 4 layers of fiber per region. And if we hit apply, it's gonna create that for us. It's gonna spread out 25 little regions with 4 layers each of fiber. And we can see here this significantly reduces the cost and print time while we still get fiber throughout the part. It's just not throughout the entire part now. So you can see here if I click through on our 2D view, I can count 1, 2, 3, 4, and then the next layer will not have fiber until we get to our next region. And then we count again, 1, 2, 3, 4. So we've effectively placed our groups of fiber throughout the part. So this part's going to be really strong and resistant to bending in this direction up here. So this is ideally how you'd want to print this part. So this is the basics of the fiber routing, and kind of we've seen all the features we have here. You know, one other feature that we can do is to selectively put carbon fiber in the part. So let's say here, I don't want any fiber in this region whatsoever, this region I'm circling. And we can do that with this new sketch environment. So I'll select the bottom layer. I will drag up to this layer here, and I'm going to say create new override, and I'm going to remove fiber. Now, I already have a region of fiber, and I'm going to remove from that region in there. And you can see it removes it from that region, but it also removed it from here. So how do I get it to just remove it from here? Well, we'll go ahead and click add a sketch. We're going to put a rectangle right here, finish our sketch, and now we see that fiber is placed everywhere in the part except that one region. So this is really neat. This is a new feature. I know a lot of customers have been asking me this for a while and saying, hey, I just need one region of my part to be extra, extra strong. And for the longest time, this wasn't possible, but thankfully Markforged released this new feature along with some of the other features we'll see in a few minutes here. But that's one of the great things about the Markforged ecosystem is that they are listening to customer feedback, they are making changes, and the software is improving all the time. So this is a really great way to save time, save costs, get your parts strong where you need it, and leave out the fiber where you don't. So hopefully this is a helpful tutorial here, because this is something I know that really a lot of people have been using and asking about. So that's it for the fiber routing. Now let's talk next about supports and custom support placement. So sometimes support structures are necessary. Ideally, you want to design your part with as little supporting structures as possible. And just as a reminder, a support is a sacrificial structure that is built anytime you have an overhang exceeding 40 degrees from the horizontal plane. So there are cases where we may not want supports created. So for example, if we have a hole that's on a vertical face, supports will keep the hole more concentric. However, it can be challenging to remove that support material later. A lot of times customers may opt to make the hole slightly oversized and then leave the supports off, which results in a less concentric, a more oval shaped hole. But if it's oversized, it may not be a huge deal. And because that overhang region is relatively small, it's just going to be at that top part of the hole, it's not going to collapse in on itself too badly, so it will still be usable. So let's say we have a part where we only want supports on the necessary areas, and some of the areas we may not want supports. So we'll take a look in Eiger as to how we do that. So going here back into our same X-ray utility, I have here some areas which we'll talk about in a little bit why they're there, but I don't want supports in this area specifically. I do want this larger diameter hole because it does have a larger overhanged area. I do want the supports there, but I don't want them on in these regions here on these smaller M5 holes. So how can I do that? Well, if I turn off supports, it's going to turn off supports everywhere. But just like how we placed custom fiber, we can do the same thing with custom supports. And it's just as simple as selecting our region, again, clicking, one more time, selecting our region and clicking create new override and remove supports. And again, we'll put our sketch region here, and we're just we don't want any support in anywhere in this region, so we'll just hit finish sketch. And as we see, reslice and save, it's going to go ahead and delete the supports from that area. And there you have it. So I can do the same thing here at the bottom as well, where I select that region, create new override, and remove the fiber. And I'll add my sketch again to select the areas within that region. And you do have some basic options here for a rectangle and a circle. Maybe there will be more sketch options in the future, but for now, you can get by with a circle and rectangle for most cases. So, all right, now we have our part in here that only has the support in that larger hole. So that is one new feature that is very useful as well, being able to selectively put your supports where you need it. Now, there is another similar feature where you can do the opposite. So let's say you have supports turned off for your entire part and there is just one region you want turned on. Well, you can do the same thing by selecting, creating a new override, and add supports. So maybe you have an area that the overhang doesn't exceed that 40-degree angle, but you still want the support anyway for whatever reason. Maybe you have some really, fine feature or some really delicate overhang. You can turn supports on for just that region. So those are the new custom support placement features here in Eiger. All right. So the last topic of today is going to be pause at layer height. This is also a really great feature. Now, why do you want to put a pause at layer height? Well, the main purpose would be to embed hardware in your part. So let's talk about that. What types of hardware may you want to put in your part? Well, the first thing you can think of would be heat set inserts or threads. So obviously, if you're putting a metal screw into a plastic part, even if you do print a hole, chase it with a tap, and put threads in it. If you put a metal screw into that plastic hole, you're going to rip out the threads. The way to get around that is by putting in these heat set inserts, and they're very cheap. You do need to have a soldering iron. Basically, the way it works is you take these heat set inserts, you put a soldering iron through the top of it, it heats up, and you push it down into your part. And they work great for some applications. However, there are a few downsides and limitations to it. The first being that they are a little bit tricky to get right because when you put these heat set inserts on the soldering iron, it melts through that part like butter. So if your hand isn't straight up and down, you do run the risk of putting those heat set inserts in at an angle. And when you go to thread in your bolt, you run the risk of cross threading that. So that's one problem right there. On the right photo here, you can see this is the proper way to use a heat set insert in that you want the heat set insert to come from the bottom. So if you're tightening from the top here, you want the heat set insert to be at the bottom so that as you apply torque to this bolt, it's going to pull up into the part. If we had the bolt the other way around and you tighten this, it can very easily pull these heat set inserts out of the part. So that's no good. So that's a problem when you don't have a hole that you can access the back side of. So if you have a blind hole where you can only see the top of, what's the solution there? Well, the solution would be to insert a captive nut inside of your part. And Markforged makes this really easy. As you know, the build plate on your Markforged printer is removable and it goes back in place with a repeatability of 10 microns, which is extremely accurate. So you can pause mid-print, and in your design, you would put a pocket for a hex nut or a square nut. And we'll see how we can insert the pause, but when the printer pauses, you can take the print bed outside, take it back to your desk, insert your nut or your hardware, put it back into the Markforged printer and hit resume. And what it's going to do is it's going to enclose that nut, enclose that hardware inside of your part permanently. So it doesn't matter what way you're tightening from, that thing's not coming out. Now, there are a couple considerations when we are designing in this way. The first being that you want to make sure that the pocket for the nut is ever so slightly deeper than the thickness of that nut. If you put a nut in there that's made out of metal and it's sticking up, you run the risk of the metal nozzle colliding with the metal nut, and you could get a dislocation error and it would fail your print. So ideally, you want to leave maybe 0.1, 0.2 millimeters of gap so that the printer can enclose it without actually hitting that piece of hardware. So let's go ahead and take a look in Eiger and see how we can do that. So you may have noticed in my part here, I have, go back here, sorry. You may have noticed here, I have these weird pockets in here. Why do I have those? Well, that is to talk about this embedded hardware. So what I'm going to do here is I'm going to first put this part in this orientation, and you'll see here, it's going to delete my overwrites. That's okay. And I'm going to go back into the X-ray view here, And we'll see that I have created an internal cavity in this part. And it is going to try and fill that internal cavity with supporting material, which we do need to turn off. But if I kind of scroll through here, you can see that there's this cavity inside for that nut. So I need to do a couple things to get that nut into the part. The first thing I need to do, again, is turn off the support structure. So I'm going to select this region here, and I'm going to go ahead and say remove supports and add the sketch, select this region, and finish. So now I've turned off the support structures. Hopefully this goes without saying, but if you have a support structure in that cavity, then you're not going to have room to put the nut in, and trying to remove that support structure mid-print is going to be not ideal. So if you do forget to turn off supports, you probably can remove that support material, but it does make life a little bit harder. So that's the first thing. Now we want to tell the printer to pause so that it doesn't completely close off that cavity, so we can actually put our nut in there. And that's really easy to do as well. All we need to do is go here to the 2D view. We'll go to where the top of that nut is. So if I scroll through here, I'm going layer by layer. You can see here, this is the last layer of the cavity before it starts putting the roof over it. So I'm going to go to this last layer here. I'm going to click Create New Override and click Insert Pause. And that's literally all you have to do. When you insert that pause, you hit print, the printer will automatically stop and prompt you to insert your hardware, or basically it'll let you know that it's paused. You can take the bed off, insert your hardware, and put it back in place. So that brings me to one other point about this. You may notice that these cavities here are actually different in shape than this hexagonal cavity down here. Well, why is that? So earlier we talked about putting the part on its side, right? So now we have a cavity that's no longer on a horizontal face, but it's now on a vertical face. So when we're doing that, there's an extra consideration, right? You need to be able to drop the nut straight down. So you do have to kind of remove, you don't get all 6 sides of the hexagon holding that nut in place. So there's 2 ways around this. The first way would be to use a square nut, and these are optimal because they have the sharper corners and they are less likely to turn in place. The other would be to design your slot like I have done here, where you have 4 sides of your hexagon being supported. You do have these 2 sides that really have nothing above it, excuse me. But you see what that looks like here in our X-ray view. Overwrite again. Whenever you change the orientation, it's going to go ahead and delete your settings just because it can't reapply it in the same way. So if I go into here, you see I've created that same type of cavity as well. So I would do the same thing where I select this region, I click Create New Override and remove supports. And then I would go to that layer and also add in the pause so that I can drop the nut straight down. Again, you do want to leave a little bit of gap. In this photo I have here, you can see that the nut is touching that top surface there, but that's not ideal. Ideally, you'd have about maybe a 0.1, 0.2 millimeter gap to allow it to not collide. Another note too, magnets are a really fun thing to embed in your parts. We've made some cool snap together cases or parts that kind of snap together with hidden magnets in there. I will caution you on this, and I didn't know the first time around. Obviously the print head is made out of metal and it is a ferrous metal. So if you insert a magnet into your part, the print head will stick to that magnet and pull it straight out of the hole. So in order to prevent that from happening, you can always put a drop or 2 of super glue right before you put the magnet on, and that'll keep it in place. So that is one little tip there. So we talked about a lot. We talked about how to create custom supports. We talked about how to put a pause at layer height, and we talked about our advanced fiber routing strategies. So while Eiger is a very simple to use software, it is also very powerful. And as you can see, taking advantage of these features really allows you to increase your usability, strength, reduce part cost, and print time. So I hope this was useful for you all. And if you have any questions, we'll go ahead and open it up to questions now.
Yeah, so we have a couple questions. The first one is, how do I know if I have enough fiber in my part?
Great question. Okay, yeah, so absolutely. So we're talking about part strength, right? We're putting in fiber selectively, trying to figure out how to make that part as strong as possible. Um, but there is an element of intuition there, isn't it? So Markforged actually does have a solution for this, and it's called simulation. This is a more advanced feature as well. It's part of the advanced tier of the Digital Forge Complete, which we'll discuss in another video. We do have a demo out right now, but the simulation that Markforged has is really great in that it allows you to simulate a part as printed. So you can go ahead, fill your part with carbon fiber, and then apply a load case to it. So I won't go into such, I'm not going to do a full demo, but you basically create an anchor on one face, you create a load on another face, and from there, Markforged will validate whether or not this part's strong enough, and it can also make recommendations on how to make that part stronger. So if you don't have enough fiber, it'll tell you, hey, increase your fiber by maybe 20 more layers to get the strength you need. So great question, and we'll do a more in-depth dive of simulation at a later date.
Awesome. Next question, if my printer pauses at a layer for a long time, is that okay?
Ooh, okay, good question. Yes. So if you're printing a long print, and let's say you have to insert some nuts, and maybe that part needs to pause 12 hours later, right? So maybe it's the middle of the night, nobody's around. Is that going to be okay? Yes and no. So one thing to consider is that the longer your part is paused, it does have time to cool. So like anything, when it when anything heats up or cools, it does have a coefficient of thermal expansion, so it will shrink a tiny bit. And I say tiny bit because when you go to resume, if it's been more than a couple hours, you will see a very small witness line where the layers below it have cooled and shrunk a tiny bit. Um, Now, if you're not too concerned about the cosmetic part of it, then it's not a big deal. But if you really, really want this to be 100% seamless, then yeah, you should be standing by the printer, kind of schedule it around when that pause is going to be. The nice thing about Markforged is that it's extremely accurate in its timing, so you can get a pretty good feel of when it's going to put that pause in there and be ready for it. See, the print time estimates here in Markforged are very accurate. So you can go to a specific layer, and when I click on a specific layer, it'll tell me of the total print time of 6 hours and 28 minutes, this layer is about 45 minutes into the print job. So you can plan accordingly for that. So great question.